Guys, welcome once more to our YouTube channel. Today we're looking at not Littoral Mock 2023 episode 4. We hope you stick around to check out the beauty of this content and also kindly leave us your thoughts in the comment section down below. We can't wait to read your thoughts, guys. Thank you for the love, thank you for the support. Let's go. When a system initially in free oscillation is damped, the sharpness of its resonance frequency decreases, correct? Its amplitude at resonance decreases, correct? Its resonance frequency increases, not sure. Okay, but we have a diagrammatic representation here. So we have amplitude of force vibration versus frequency, right? Force and frequency. So you realize that when the force and frequency equals natural frequency, right here is when we have resonance, and that's when, of course, the system vibrates with its maximum possible amplitude of vibration. Now, I need you to recognize that. So when you've not damped the system, or when the system is just lightly damped, the resonant frequency is very sharp. But when you begin to damp the system all the way down to heavily damping it, you realize that the top of the curve flattens out, right? So the resonance frequency there loses its sharpness. And so that's why 1 and 2 are correct. Again, for 2, its amplitude at resonance decreases. That's very true. This is our resonance frequency right here, right? That's when the forcing frequency equals natural frequency. And you notice that as you increase the damping factor in the medium, or when you increase the damping force, uh, the amplitude is decreasing, okay? And so our answer is A then. A circuit consists of an air cord, core, a lamp, and an AC power supply all in series. A solid iron rod is moved into the core. Which of the following is not true? Okay, the lamp will dim because the PD across it has dropped. Correct. The iron rod will get a little warmer. Correct. The reading of AC voltmeter connector across the ends of the core would fall. Not true. It would rather increase. So I've taken our time to analyze why these answers are right and this one is wrong. But again, we're looking for the one that is not true. So our answer is 3 only, which is D. But let's talk about why these ones are not true. So I've taken our time to do some writings. We're just going to go through them together, okay? When alternating current flows through the core, a B field is developed across the core, rendering it to act as an electromagnet. As the iron rod moves into the core, it cuts several magnetic field lines per unit time, which causes an induced current to flow through the iron rod, causing it to warm up. The effect of current. That statement is true. Okay, that's basically how we're explaining why this thing gets warmed up. Okay, so you're getting an iron rod to cut across magnetic field lines that are generated as a result of propagating an alternating current through this core. So the current will be changing with time, right? So the changing current would produce what? Would produce a B field. That's why this guy acts like an electromagnet. And so when this guy goes in there, it's getting magnetic field lines per unit time. You notice that that creates an induced EMF through it, and an induced current runs through the core, through the rod. And so it gets warmed up. Uh, when the iron rod is inserted, the magnetic field line inside the solenoid is increased. This increases the inductance of the solenoid, so the inductive reactance of the solenoid increases. Okay, so this guy is an electromagnet, so I'm sending in a ferromagnetic material in there. It enhances the magnetic field of this guy. Okay, so because the magnetic field is enhanced, the inductive reactance increases, and so more PD is dropped across this guy. That's why less PD now falls across this guy, and this guy dims up as a result. So our answer there is D. When steam at 100 degrees Celsius condenses from water at the same temperature, the entropy of the surrounding increases and entropy of the system decreases. Correct. Okay. Now the problem students might have here is with the thermodynamic state, or the entropy statement of the second law of thermodynamics. And it's that, well, the entropy of an isolated system can never decrease. And guys, the catch here is isolated system. This is not an isolated system. Steam is condensing. You realize that it's losing heat to the surrounding. And so it's moving from a more disordered state, which is steam, to a more ordered state, which is liquid. And so the entropy decreases in that case, the entropy of the system. But because it's exothermic, the gas molecules around that system, they gain heat because the steam is losing heat to the surrounding, right? So they gain heat and they become more disorderly. So the entropy of the system reduces while that of the surrounding increases. That's why one is correct. And so our answer there is C, one only. Which pair of forces below are an example of Newton's third law? When a car is being towed by a lorry, the lorry pulls forward on the car and friction pulls backwards on the car. Not true. Why? Because we're talking about action and reaction forces acting on the same body, the car. That's never happening, okay? So action and reaction forces act on different bodies. When a child moves down a slide, the Earth's gravity pulls the child down and the slide pushes up on the child. Again, the same thing here, acting on the same body. Not true. When a cat jumps, the Earth pulls down on the cat and the cat pulls down on the Earth. Correct. So you have the forces acting on two different bodies. The gravitational force that the Earth exerts on the cat, which is the weight of the cat, and then the cat in turn exerts an opposite reaction force on the Earth by pulling up back on the Earth. And that's why this one is correct. So you notice that the two forces there are of the same kind, so they are both gravitational forces, all right, and they are in sync with Newton's law of universal gravitation, that any two masses in the universe would attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of the mean distance between them. Okay, so yeah, statement 3 is our answer. Then I've taken our time to do some writings about Newton's third law pair of forces, so just have some time to read through it. Pause the video, all right? So our answer there is D. Figure 20 shows the plate of a capacitor ROS joined to a battery of EMF E and with charges plus Q and negative Q respectively. Which of the following statements are correct? The electric field strength between the plates increases from S to R. Electric field strength between the plates, not true. Why? Because the region between the plates of a power plate capacitor is an example of a uniform field. So the field strength there is uniform, it's a constant. The energy stored is half Kelvin squared. Not true. Energy stored is either half Kelvin or half CV squared. So this square spoils everything. So this one is not true. The electric potential between the plates decreases uniformly from R to S. Correct. Okay, from R to S, higher potential to lower potential. So it's decreasing uniformly. Correct. So I've done some writings. Again, take our time to pause and then read through it. Our answer there is D. Temperature of the axis of an unlapped metal bar supplied with constant heat at one end, displacement of points from the heat hotter end of the bar. Again, it's unlapped, right? So if it's unlapped, temperature would vary exponentially across the length of the metal bar. But if it was lapped, then you would basically just have a straight line with a negative slope from this temperature at the hotter end all the way to temperature at the colder end. And so our answer there is B. Young modulus of a piece of wire, cross-sectional area of the wire. Okay, so Young modulus is FL0 by AE. Again, you notice that if I want to plot E, Young's modulus against A, that would be an inverse relationship, right? So inverse relationships, of course, graphically are represented like this. And so since Young's modulus is always positive, we're going to use the first quadrant, and so our answer will be D. Momentum of a photon, wavelength of the waves associated with the photons. We just use de Broglie's equation. Momentum has an inverse relationship with wavelength again. And so our answer is basically A, right? Tension in a loaded spring hanging from a ceiling when slightly displaced vertically from its equilibrium position, displacement of the load. All right, so the tension is K E plus X, okay? So we expand that, we are going to have T equals Kx plus Ke. And so T is our Y, X is our X, right? And so C intercept on the y-axis is Ke, which is positive, and so that's the graph, and so our answer is B right there. Energy stored in the plate of a power plate capacitor of capacitance C, potential difference V. So energy is half CV squared, right? So you notice that half C is a positive constant. So this Y against a positive constant multiplied by X squared. So this is a quadratic curve whose turning point at the origin and yeah, has a minimum turning point. So that's the quadratic curve there. But since we're interested in the positive part of the first quadrant, let's talk about energy. So you notice that we're going to use just this portion, and so our answer is B. Thank you guys so much for checking our content. It's always a pleasure to have you here. Thank you for the support. Thank you for the love. We can't wait to see you soon.